Oh, welcome back to our course, Advanced Quantum Mechanics. This is lecture 9. Let's see, where are we now? Well, we know how to go from Hamiltonian to the equations of motion, canonical commutation relations, Hermiticity condition, and then we solve these to obtain the linear map valued solutions as functions of time. This is the pi and the pij of t, etc. And of course, then all the polynomials f hat of x hat of t and p hat of t, and so on. And then we found that if we introduce an initial state vector psi, then we can calculate predictions x bar I of t, which are number valued, including for the f bar of t. And remember too that this is including predictions for delta x of t, delta p of t, and so on, delta f of t. And why is it that we can calculate these? Well, because we can calculate the expectation value, the predicted values for any observable. So in particular, delta f of t squared, so that's the variance. We can calculate that because we can calculate the prediction for the square and subtract from it the square, the square of the prediction. Right? So, all right. What we will be concerned with today, though, is this part. This vector psi, the initial state vector of our system, the vector that encodes the initial conditions that we choose. It turns out that we will need to upgrade our understanding of the vector space on which in which the psi live. We will need to study Hilbert spaces, and somewhat thoroughly, so that we are then able to move freely between the bases of this Hilbert space and, for example, between discrete and continuous representations, and that we are comfortable at the end to work in any representation we want, while still seeing the big picture of what the physics is that is working behind the scenes, bases independently. So what we will need to study is Hilbert spaces. We need to study Hilbert spaces. You've, of course, heard of Hilbert spaces, but maybe not of the subtleties that come up when you study Hilbert spaces. The discipline that you would need to study to learn everything about Hilbert spaces is functional analysis. So we will do a bit of functional analysis today, and that will be pretty mathy, but we'll need it so that we are better prepared than for the physics that comes after. So we start with the definition. Before we get to Hilbert spaces, we have to make quite a few definitions, actually. We have to build up the structure of the Hilbert spaces. The Hilbert spaces are vector spaces with extra structure. And now we will introduce, little by little, that extra structure. So first definition is that a set, or any set H, is called a complex vector space if A, it possesses an operation which maps from H cross H, I'll explain in a moment what exactly that means, into H, called an addition which obeys the axioms of a commutative and therefore also called abelian group. And if, and there will be a point B that I'm getting to in a moment, but let me just tell you something about this part of the definition. So we want to define what kind of sets are called complex vector spaces. And we will have two sets of conditions, A and B. And condition A says that our set H needs to possess an operation from H cross H into H that has certain properties. Now, what is H cross H? This is what is called, this is the set of all pairs of elements of H. So this is equal to set of all pairs. Let's call it V and W with V and W in H. Because that's the definition of what this cross means here. It means simply just the set of all pairs where each element of the pair is taken from H. So the condition here is that a complex vector space is a set which possesses an operation that takes two elements of our supposed complex vector space and maps them into an element of that complex vector space, which has the properties which fulfills the axioms of a commutative group. Now remember what a group is. A group has an operation, in this case it is called an addition, which is associative, and we want an inverse, and we want a neutral element. And in this case also commutativity. It's quite common that commutative groups are called additions, or that the operation of a commutative group is called an addition. But you can call it whatever you like. It's just a name. Remember that this is literally just a name. This is important. I can't emphasize that enough, that in mathematics, you're never supposed to just work with intuition for what something might mean, like an addition. In this definition that we make here, the word addition is defined by what's coming afterwards, right? It says, which obeys the axioms of a commutative group. Then it is called an addition. You need not remember anything about any other addition that you've seen before. This is completely self-contained. Okay. I'm being a stickler about this today because it's a relatively mathematical lecture today. Right, so B, what other condition do we need? We need that H possesses another operation too, namely what we traditionally call a multiplication or scalar multiplication, which is going from pairs of a complex number and an element of the vector space into an element of the vector space, right? So C cross H is by definition the set of pairs where the first element of the pair is a complex number, the second element of the pair is an element of the set H. And this multiplication needs to obey several axioms, namely obeying for all V and W in the set H, and for all alpha and beta complex numbers needs to obey, this product needs to obey that alpha plus beta, remember these are just complex numbers, multiplying one of those elements V is alpha V plus beta V. And we also require that this product, and in fact the multiplication that we had earlier, that the multiplication and the addition that our set H has obeys also that alpha V plus W equal to alpha V plus alpha W, you know, the kind of thing that you would expect from linearity. And that alpha beta acting on V is equal to alpha and then beta V. Okay, so here we first multiply two numbers and then multiply them on the vector V. And here we first multiply one number on the vector V, get another vector, and then multiply that with alpha. And also 1 times V is supposed to be V. All right, these things are not trivial. You can always cook up sets for which this is not fulfilled. We do this so abstractly because, and I'll stress that again, you see, I know that some of you are mathematicians, some of you are physicists. I'm talking to the physicists today, mostly, trying to get across some mathematical intuition for these things. So notice, when I don't hold the pen very well, then the writing gets even worse. So every set obeying these axioms is called a complex vector space. Now you might say this is repetitive. You told us that before, right? And I did. But I want to highlight every set because I will show you soon a set of which you would not have expected that it obeys these axioms. Well, maybe if you knew beforehand, but okay. So let me give you an example. What could be a set that is a complex vector space? Well, let's say H1, so we call it H1 just to give it a first name because we will have several examples. H1 is, let's say, the set of complex 3x2 matrices. So how do they look like? They look like this. We have here M11 is a complex number, then we have M12, M13, and then we have M21, M22, and M23, right? This is all complex numbers. You can add them. I mean, there's a natural addition for the set of these complex 3x2 matrices, and that's addition component-wise. And there's a natural multiplication with complex numbers, which is also component-wise, right? You just multiply the matrix by multiplying every matrix element with the complex number. So you can easily check that it obeys the axioms. But then here is a different one. H2 is, let's say, the set of complex valued functions f, which map r to the power 27 into c. Or we don't really need that many dimensions here. Let's just say r2 into c, so that it doesn't get too messy. So what would be typical elements? Well, for example, f of x and y equal to cosine of x plus e to the power y, x to the third. Let's put an I in here. All right, that would be a complex valued function over R2. Now, if you add two of these functions, two of such functions, complex valued functions, well, you get another one. And it's this addition obeys the axioms that we required of an addition above. Namely, it's a commutative group. You see, for every function that you add, you can always add the negative of that. So you have an inverse. And you have the neutral element, which is the function that maps everything into 0. And also, you can multiply any one of those functions with a complex number, you get a function again. So you now have a complex vector space. Now, H1 has how many dimensions? H1 is a 6-dimensional complex vector space. H2 has how many dimensions? Well, infinite dimensions, obviously, because we can write down infinitely many different functions, complex functions over R2. So you see, the axioms can apply to a wide variety of sets. And this is where math derives most of its power from this abstraction. And now we'll get to one of the most important examples here, which is something that we should now notice, namely that given any complex vector space, so it could be any one of the two above these examples, or really any other complex vector space. Given any complex vector space H, we can construct a new complex vector space from it. We can construct a new, a new complex vector space from it. And in quantum mechanics, this is going to be super ubiquitous. We do it all the time, and we call it H star. H star is also just a complex vector space, but it's derived from H. And how do we do that? How? Well, consider a continuous linear map. Let's call it R, that maps R maps elements of H into complex numbers. Okay, so what we have is that R takes an element of H, such as V, and maps it into R of V linearly. Right? So, i.e., we require that R of lambda V is lambda R of V. So let's assume we have such a linear map. Let's look at an example. Start with H1. Remember that was the complex vector space of 3 by 2 matrices. Then, let me write down a linear map from H1 into the complex numbers. So R maps H1 into the complex numbers, namely R takes one of those matrices, with M11 to M23 up here, and maps it into 7M11 minus I M12 plus M22, right? This number is in C, and we input a matrix, we output a complex number, and the whole thing is linear because we have M11 is linear, M12. We don't have any powers of the M's. We don't have any non-trivial functions in the M, so the whole thing is linear. If we do R of the sum of two matrices, we get the sum of the two complex numbers. If we do R of 5 times the matrix, we get 5 times the complex number. So R is one of those linear maps. Let's do another example, this time with H2. Start with H2. Oh, by the way, so what we have is that R is an element of H1 star, right? That's the, sorry, we will get to this in a sec. Okay, so we start with H2 now. Remember what H2 was. H2 was the complex vector space of functions that map R2 into C. So our R is mapping now H1. I mean, this R has nothing to do with the R above, right? So let me call it R tilde. So this is mapping H1 into C, namely how? Let's say that R tilde is mapping our function f. F is a function over the xy plane, complex valued function. It's mapping that into, let's say, the integral for x equal 1 to 3, y equal 4 to 100, and then we have f of x and y dx dy. Let's put an I in front of it, doesn't matter. So what do we have? The R tilde maps a function, that is to say an element of H1, into a complex number in this way. And as you can convince yourself, it does so linearly. If we take R tilde on the sum of two functions, f and g, we get just the sum of the output complex numbers. If we multiply f with a number, we can pull that out because the integrals are linear. Okay. So now we are ready for the definition that I was anticipating, and then erased it again. So now we consider the set H star, which is defined to be the set of all R which are continuous linear maps, which are continuous linear maps are from H into C. Then, so I give you examples of R and R tilde for H1 and for H2. But for each one of those complex vector spaces, be it H1 or H2, you can of course write down many, many, many such linear maps. And this collection of all of them, that's what we then call H star. And the beauty is that H star is itself a complex vector space. So one can show H star is itself a complex vector space. What does that mean? It means that if you have not just R tilde, but also another element S tilde, which is also a continuous linear map from functions into complex numbers, then you can add them, right? So you apply R tilde on F and add to it what you get when you apply S tilde on F. That's the same as if you added first R and S tilde and then applied that to F. And you can multiply them and so on. So H star is itself a complex vector space. And H star is called the dual space to H. Now you may wonder why we have here the word continuous in this. Why would we have the word continuous here all the time? It's actually, it turns out it's important. One might think from the intuition of linear algebra that every linear map is obviously continuous. Well, in infinite dimensional vector spaces, linear maps don't have to be continuous. In fact, most of the linear maps that occur in quantum mechanics are not continuous. Like the position matrices, the momentum matrices that you saw. They're all linear maps, they're matrices. But one can show, and we will see that later, that they are not continuous. In fact, weirdly, they are not continuous anywhere. They're discontinuous everywhere. But we should not worry too much about this. This is all under control, but it's strictly speaking true that they're not continuous. Now in quantum mechanics, see what I said is just general math. But now in quantum mechanics, we work with a complex vector space H, and we denote its elements by kets, right? So we write V in H, right? So all elements of our complex vector space of states, of initial condition states, so V or psi of H, that's what we write. And then we call them and call V a ket or ket vector. Now, because H is a complex vector space, we also have an H star, a dual vector space. And then we denote the elements of H star by this. We would, for example, write W, and this is and call it a bra vector, such that we have a bra and a ket, and together they will form what is called a bracket, and call it a bra vector. So we will write W as an element of H star. This is quantum mechanical notation, and in pure math it wouldn't be written this way. Further, for let's say R in H star, we would write in math that R is mapping a vector V from H into R of V, because it feeds on that input vector, and this is an element of C, right? This is how we would write it in pure math, because R is an element of the dual complex vector space. So it is a map that takes an element of the original vector space H and maps it into a complex number. But in quantum mechanics, in QM, we write R of V differently. We write it as R V. Okay, so when we have the R on the left and the V on the right, what it really means is that R is a dual vector. It feeds on the V and maps it into a complex number. This is Dirac's bracket notation. This is Dirac's bracket notation. Now in quantum mechanics, the complex vector spaces have even more structure than what we just covered. So let us add to this, because our final goal is, of course, to arrive at Hilbert spaces. Definition. Assume that we have a map which we call dagger, and for now we call it dagger. It will be called Hermitian conjugation for vectors, and it has the property that it maps the complex vector space into its dual. Assume that we have a map, dagger, which maps the complex vector space in its dual. So that is to say that this will map vectors v into v dagger, which we will write as v. So this means that if we have such a Hermitian conjugation map, then we are having a correspondence between vectors in H and vectors in H star. Every vector in H uniquely maps into a vector in H star, and by tradition, we apply the same name to it. So V gets mapped into V, but it's a vector in the dual complex vector space, and so it should not be confused with that one. And we wanted to obey certain conditions. So assume a map dagger obeys that now you might expect, well, we want it to be linear, right? But not quite. We wanted to obey that this dagger map maps R times a vector, let's say V, plus S times a vector W, gets mapped into the complex conjugate R times, oh, now I have to turn it the other way around, of course. So this is a V plus S star W. All right, so we want that this dagger map maps vectors in H into vectors in H star in an anti-linear fashion, because R cannot simply be pulled out. We can pull it out of this action of the dagger, but it gets complex conjugated, right? So we would have, for example, this, just to make it clear what this is, this would normally be written as RV plus SW, and then the dagger of it, right? So this then is R star V plus S star W. And this supposed to hold true for all R and S complex numbers, and for all V and W in the original complex vector space. Then, assume we have such a Hermitian conjugation map. Then, given the Hermitian conjugation map, we define a map S, which will be called the scalar product map or inner product map, H cross H into C, Cartesian product H cross H into C, which maps two vectors V and W into V W, which is a complex number, right? Remember what this was? This was V of W, because the bra of V is a linear map that maps vectors out of H into C. Now, assume that the dagger, the Hermitian conjugate, the dagger map that we defined above is such that, remember, it maps V into V, or dagger is mapping H into H star, is such that the following holds true. Such that U, and then we have alpha V plus beta W is alpha U V plus beta U W, and we want that V W complex conjugated, because remember that the bracket of V and W is a complex number, because V is a dual vector that evaluates, that feeds on W and maps it into a complex number. We want that this is equal to W V, and that V is larger or equal to 0, and we want that V is equal to 0 if and only if we have that V itself is the 0 vector. So assume that this is the case, that we have a map from the complex vector space H into its dual such that the map S obeys these axioms here. Then dagger is called a Hermitian conjugation, and and S of V and W, which is VW, is called an inner product or scalar product. On H. If you have taken some functional analysis, you may have seen the definitions a little bit differently organized. Still the same definitions, but a little bit differently organized, where you start with the inner product and then you derive the Hermitian conjugation map, but following Dirac, it's more natural to start with the Hermitian conjugation map and then get the inner product from it. Okay, now we are almost there with the Hilbert spaces. So the definition is that a complex vector space which has this structure, a complex vector space H with this and a scalar product is called a inner product space or a unitary vector space or unitary vector space or also a pre-vector, a pre-Hilbert space. Now, if what you're interested in is, for example, quantum computing with a finite number of qubits, then you're fine here. That's fine. You can do all of quantum mechanics with complex vector spaces that are also inner product spaces. So you just need this emission conjugation map and inner product. But if you're interested in how matter moves, then remember that the X and the P can only live on infinite dimensional vector spaces. And in quantum computing, we try to isolate a finite subset of dimensions and work with that. For example, spins and so on of particles. But fundamentally, of course, we have infinitely many dimensions in our vector spaces, and therefore we have to move on from here to actual Hilbert spaces. Now, what extra structure might we need to get to Hilbert spaces? Hilbert spaces are important, an important concept. The structure of a Hilbert space is very important in order to keep tabs on infinite dimensions, in order to keep things under control when you have infinitely many dimensions. You can think of it this way. For practical purposes, for example, when we have column vectors with infinitely many entries acted upon by matrices that are infinite by infinite, well, then whenever such a matrix acts on a column vector, then you have to do all these multiplications of the components of the column vector with the matrix elements. And there are infinitely many of those. So you have to do a series. You have to sum things up. You can imagine how, if you take infinite sums, if you take series, that there could be issues of convergence. There could be issues of a non-commutativity of limits when you have several of these sums. And then when you have sequences of vectors, and the vectors have infinitely many entries, and like column vectors that are infinitely long, infinitely many entries, then summing the product of a matrix on a column vector may not commute with running through a sequence of column vectors or a sequence of matrices. So in order to keep these things under control, we need extra structure. And that's a topological structure. We need to understand what it means for things to converge in infinite dimensional vector spaces. And for the purpose of understanding convergence, we need a notion of distance, because we can only define that something converges to something else if we have a notion of distance between elements of the set in which we want to take limits. So for this purpose, we now define, first of all, the notion of a length of a vector. So the length of a vector or norm of the vector is defined as length of V is equal to V to the power of 1/2. Remember that from the axioms above, we know that this is a positive number. Okay, so that's the norm. And we say, of course, that a vector is normalized if its length is 1. We had that before, we said that before. But now we will use the definition of a length to define to make a definition of what is the distance between two vectors. right? And what we mean by that, of course, is intuitively speaking, if our vectors were intuitively something like this, then the distance between two vectors is this distance here, right? The length here. But keep in mind that our vectors may have nothing to do with arrows. Our vectors could be functions. Because remember, if you have a function space, well, you can add two functions, get a function. You can multiply functions with some number, you get a function. Function spaces obey the axioms of a vector space, and they are definitely nothing to do with arrows. Anyway, we want to define the distance between two vectors now. And for that, we use the notion of length. So we say that the distance between two vectors, v, w, or let's call it d of v and w, is defined as the length of the difference vector, as distance of this vector to that vector is defined to be the length of v minus w. Okay, so clearly if v is equal to w, the distance is 0. And only if v is equal to w. Now that we have a notion of distance, we are ready to define the notion of convergence. Namely, we say that a sequence of vectors and let's write this sequence as Vn, n equal 1 to infinity, converges to a vector A, just to give it a name, arbitrary, if the limit for n going to infinity of the following sequence of numbers goes to 0, and the distance between the vector Vn and it's the distance between them. The distance between Vn and the vector A goes to 0. Right? Remember what this is. This is equal to the length of the vector Vn minus A. Okay, so we say that a sequence of vectors Vn converges towards a vector A in our pre-Hilbert space H if the sequence of distances between these vectors goes to 0. So for example, you could imagine in quantum mechanics that you have a vector, that you have a sequence of vectors that describe a sequence of experiments that you may want to do. For example, check whether the system is in the state V1, and then you do an experiment where you check whether it's in a state V2, and then you check whether it's in a state V3, and so on. And these subsequent states might describe, for example, increasing levels of localization. You measure, is the electron in a big box? Is the electron in a smaller box? Is it in an even smaller box? And so on. So you, for example, that would be one way of arriving at a sequence here. So now we have the notion of convergence of a sequence of vectors. And now we will do a definition which seems like it's equivalent, but for a very subtle reason it's not. And that's super important, and that makes the difference between pre-Hilbert spaces and Hilbert spaces. So we define that a sequence of vectors Vn n equal 1 to infinity is called a fundamental sequence. Or it's also called a Cauchy sequence. And maybe you remember now from earlier calculus what these things are for numbers. Now we do it for vectors. If the limit for n and m going to infinity of d, the distance between Vn and Vm, goes to 0. So this looks very similar to the definition that we had earlier of convergence. I mean, what does it mean if the distance between successive vectors goes to 0 as n and m increase further and further? It means that that as you go down the sequence of vectors, they become more and more similar, right? These vectors become more and more similar. They become closer and closer and closer. So you would expect that every fundamental sequence is convergent, just because subsequent vectors become closer and closer. So we would suspect that fundamental sequences all have some vector A belonging to them towards which they converge. But that is not trivial. That's not generally automatically true. So let's ask, are all Cauchy sequences convergent? The answer is no. It depends on the space H. For some spaces H, it is true, for some it's not. And the definition that is crucial here is that a pre-Hilbert space, so a complex vector space which has an inner product and Hermitian conjugation, a pre-Hilbert space in which all Cauchy sequences converge. That is to say, if subsequent vectors get closer and closer to each other, then there is a vector towards which they converge. A pre-Hilbert space in which all Cauchy sequences converge is called a Hilbert space. Now, you may wonder, does this ever come up in practice in physics? And the answer is yes. Remember that as how we saw at the beginning of the course that the X and the P cannot be represented as finite dimensional matrices, but they can as infinite dimensional matrices. That showed us that there are phenomena that can only happen in infinite dimensional vector spaces. And we introduced the notion of Hilbert space here to make sure that we keep things under control. And I will later explain examples where these sorts of things actually make a difference for practical measurement purposes. For example, the unsharpness of a microscope or of a telescope. The sharpness of a microscope and telescope or any optical device is fundamentally limited by the uncertainty principle. Depending on the opening size of a microscope or a telescope, there is a best possible idealized resolution that is not perfect. There's always a certain minimum amount of fuzziness. And that has a mathematical representation in terms of this sort of things here that we are talking about today. What I'm referring to goes beyond just the regular uncertainty principle. All right, so let me give you a bit of intuition or just a reminder that you have seen this sort of thing happening before. Namely, recall. Consider the rational numbers. Consider the set of rational numbers. So all fractions. You can view this as a one-dimensional vector space, right? Where a column vector with only one component, if you like, where the components are rational numbers, if you like. Okay, so consider Q, set of rational numbers. And now consider this sequence. Consider this Cauchy sequence. So I'm going to write down now a sequence of numbers, let's call them Qn, where n is equal to 1, 2, all the way to infinity. Consider this Cauchy sequence, which is defined by Q1 is 3. Q2 is equal to 3.1. Q3 is equal to 3.14. You might be seeing where this is going. Is equal to 3.141, and then Q5 is equal to 3.1412. 15, sorry. Yes, actually I know 50 digits, but I made a mistake at the fourth. Anyway, it goes on like this. And then you see what's going on. This sequence of numbers is a Cauchy sequence. It's straightforward to prove that. It's of course the digits of pi, right? It's the successive approximations to pi. And clearly these numbers get closer and closer to each other because they differ only further and further down the road here at higher digits. So this sequence of numbers is a sequence of numbers that get closer and closer and closer, and they are forming a Cauchy sequence. But is there a number towards this sequence converges? No. You might say, well, it's pi. Yeah, but pi is not a rational number. So in the set of rational numbers, this sequence is not convergent. It is a Cauchy sequence, but it's not convergent because there's no number towards which it can converge. That's the reason why we invented real numbers. The rational numbers are not complete. You have this problem that there are two notions of convergence that are not the same. You have Cauchy convergence, Cauchy sequences, which say things get closer and closer and closer, arbitrarily much. And yet you don't have something that it converges to. So that's why the real numbers were invented in order to have that the intuition comes true, namely that Cauchy sequences ought to be convergent. So we introduced R as the completion of the rational numbers. Namely, we introduce now new numbers which are obtained as for every Cauchy sequence, we introduce an element. And that's a real number. A real number is, by definition, a Cauchy sequence. In fact, an equivalence class of Cauchy sequences. Okay, so point is, in Hilbert spaces, we want that Cauchy sequences are convergent, and now you know what a Hilbert space is. So we will soon launch back into physics, and also I'm not intending to examine you on in the midterm or final on these pure mathy things, but I thought you need to know that anyway. I mean, a few things I might ask you, but no great details there. All right, so I see you on Wednesday then.